What is it again?
But I mean, I don't have $5.
The Paradex, sorry. The Paradex PTT QG.
You literally want to.
Wait, is that the way to yesterday?
My wallet.
Okay.
Oh my goodness, I love your cat.
Thank you.
My cat is having a
Good
tea
man.
party today.
That makes sense if I don't think about it.
Yeah.
All right. I'm going to close that because they've been doing a lot of today. I don't know. I think there's just a man in the room that's frustrated. That's what it sounds like.
It's because you broke their brooms. I was gonna call them sweepers.
Oh, the brooms. Oh, I thought you said sprues. I'm like, what is a sprue? All right. Brooms. Yeah. I can't hear good. So, hey, I was going to show you. We'll come back over to this in just a sec. So I posted this on Canvas yesterday because a couple people asked. On the exam day, when you're taking 35 multiple choice questions in 45 minutes, you're probably not going to want to take the time to actually calculate out the center of mass. But I went ahead and I threw those on here. I don't know why I was struggle busting so hard. What I ended up in the end doing was treating each element, each little, whatever you want to call that segment, as an M, rather than calling that an M over 2, and I could make the math happen there. That's how. So I was able to get to 15/14ths and 6/7ths. So it's there if you want to check it out. If not, I'm not mad at you, because on the day you just need to be able to say things like, well, it would be in the center at 1,1 if that segment was there up top, but taking away that segment, it's going to make the y less than 1 and make the x greater than 1, and then go accordingly. That's how you solve it on the day. But I have the actual solution on there for you if you want that too. Okay? So we're back over here on the Pear Deck, PTT QG. Let me hide this thing because it's going to bug me. And hey, 15 students are connected. Start class when you're ready. I'm ready now. All right. So yesterday we looked at all these slides and then I shared it with you. And so this was what we looked at as far as how to use integral calculus to find the center of mass, which Cole was just asking about that. Danny, did you have to do that on the test last year?
There was that one question.
Where you had to use integral calculus to find the center of mass? Was it like the multiple choice ones that I was talking about from yesterday? Multiple choice or free response? Oh, balls. I better go look at that. Okay. Well, if they did it last year, you won't have to do it this year. So, yeah. All right, we looked at this. We talked about the bad problem. Oop. So it wasn't like this business. It was like a little bit more find the center for that one. Okay, cool. Something to do this afternoon. All right. So back to why you did such a crappy job on the last practicum lab where you had to predict where the ball was going to land. Okay. The problem was that we weren't accounting for our LOL was incorrect, more or less. Okay. Our LOL for that was basically saying that, let's see, AP5, let's do a new page, let's call it EK Rot. All right. The assumption was that for your LOL, you started off with the energy stored gravitationally, and you ended up with it stored kinetically. Okay, this is for the ball rolling down the incline here. This is A, and that's B. That was our assumption. In reality, what percentage of energy ended up as EK and what percentage did not end up as EK? Run it by your neighbor real quick. Do you remember ballpark?
I think ours was like 30%. 30%?
Yeah.
I don't remember. I think it was 30%.
About 30, says Emma?
Yeah.
Somewhere in that ballpark, right? Okay. And initially, everybody and their mother, except for Emma, thought that that energy had been dissipated by friction. How did I demonstrate that that was not the case? What did I do? Use my thermal energy camera that I don't have yet. Nope, didn't do that. Cool. It must have been really, what do I want to say? impactful. Dorney?
Yeah, like when it rolled down, we went up the ramp and went the same distance.
Yeah, okay. Roll it down the ramp, and it rolled up to the same height on the other side, almost like a bowling. Did we do a bowling ball or something here ever? No. Should have done that, sorry. Anyway, yeah, the ball gets up to the same height on the other side. That's evidence that the energy is not dissipated, it's stored somewhere. And then eventually we got around to the idea that it was stored in the rotation of the object. That's what's scary, okay, is there's some injury stored in the rotation. And it's really just a different way of accounting for kinetic energy, okay? Because if you think about a rotating object, so if we look at the rim of this thing and we look at maybe just focus on like this particle of mass right here, it's, stay put, okay? It's got some tangential velocity relative to the axis of rotation. And so we would just take 1/2 the mass times that tangential velocity squared, and we get the kinetic energy of that little bob. And then we just add up the kinetic energy of all the little bobs based on their tangential velocity squared, and we'd have it. We'd have the rotational kinetic energy, okay? In reality, that would be kind of cumbersome in terms of the calculation because you got all these different R's and they go along with all these different V's here. So a cleaner way of thinking about this, rather than the tangential velocity, recognize that all points on that rotating object have the same angular velocity. So I kind of have a different little thing going on here. So if you recall from back in the day, V tan is 2 pi r over big T. Omega is 2 pi over big T. So if you see what's going on here, V is just R multiplied by omega. Okay, alternatively, omega is V tan over R. We're just using that here. So where I have V tan squared, I'm going to end up dropping in here R squared omega squared. Okay, so you see down at the bottom, that's what we're, stop mouse overing. So that's what we're summing down there at the bottom. 1/2 m1 times its radius from the center squared times its angular velocity squared plus 1/2 of mass 2 times its distance from the center of rotation squared times omega squared. All the omega squareds are the same, so I can factor that out. And so the sum that I have to perform here, I've got to sum all these mr squared terms. That's kind of like when we did center of mass yesterday, and you're summing all the mr terms, or mx as it was, my. Here it's mr squared. So it's going to operate just slightly differently when we get to the calculus part of it. Okay?
Wait, what does that show us?
What does who show us?
What does that equation show us?
Down here, I'm just finding all of the kinetic energies of all the little bobs, all the little particles throughout the object. That would be 1/2 m times v squared, right? That's kinetic energy.
Mm-hmm.
Because it's rotating, though, I'm substituting in place of v, I'm putting r omega. And so that's the difference between the bottom two lines of the equation. I'm going from v squared to r squared omega squared.
So it's giving you kinetic energy.
Kinetic energy, just like we were calculating it before. You're just taking 1/2 the mass times velocity squared. Because it's rotating, I'm just doing it a little bit differently.
Okay.
I'm trying to find a way to use angular velocity because that's the same for all the particles. To do that, I end up with having to sum all the mr squared terms, okay? So this sum of all the mr squared terms thing is called the moment of inertia, okay? So if Ethan puts his big bear paws on the disc and the hoop in front of him, can you palm those things? Yeah, oh my gosh, look at those piano fingers. Wow, all right. And if you hold them out in front of you and twist them, try to twist them vigorously,
Okay.
what do you notice?
This one's harder to twist.
Yeah, it's harder to twist. And if you kind of show the fine folks at home which one is which here, okay? So the one that's hoop-like, that's harder to twist. They're the exact same mass. If we have Daniel give them the shake test, then you can just use your little hands to hold them and shake them. There we go. Okay. The shake test, this was our classic test to compare the mass of objects. Because something that's more massive is more resistant to a change in motion. Okay? Whereas when Ethan palms them and twists them, it's not the mass of the object that he's experiencing. It's the rotational inertia, okay, or the moment of inertia. It's how resistant is it to a change in rotation. And again, all we're doing is summing the mass of the particle times its distance from the axis of rotation squared for all the little mass particles that make up the object. So then when we're talking about rotational kinetic energy, sum of mr squared in the previous slide, I'm just replacing that with I. I is the letter variable that represents the moment of inertia. And then omega squared. But again, it's not any different really than the 1/2 mv squared kinetic energy we were dealing with previously. It's just now we have flavors of kinetic energy. Now we have one kinetic energy that's due to the translational motion, and we have another type of kinetic energy that's due to the rotational motion. So if something's doing both of those things, we've got to account for both of them. Yo.
Where does the equation for moment of inertia come from? How do you get that?
So that's coming from here. Okay, like in regular kinetic energy, it's 1/2 the mass times the velocity squared. But because we're dealing with it rotationally, in place of v, we're substituting in r omega. It's equivalent. Okay, and so when I square it, I end up with r squared omega squared. For all points on this thing as it rotates, they're going to have the same omega. So I'm factoring that out. Okay, and so what I'm left having to do is sum mr squared for every particle that makes up this disk. Every little itty bitty particle has some mass and is some distance r away from the axis of rotation. And so the name that we give to this sum is the moment of inertia. It's going to behave in here like mass behaves in the 1/2 mv squared equation. So again, like in terms of conceptually how you want to factor this in, it's operating just like m operates in 1/2 mv squared. But when we're rotating, we care not only how much mass, but where is it located relative to the axis of rotation. Dimensionally, you're taking mass times the distance from the axis of rotation squared. Your units are kilogram meters squared. And I'm aware of something from POE that was called moment of inertia but had different units. Yeah? Sweet. I'll have to talk to Dr. Audi at some point and figure out what the heck that's all about. But this is the physics one. So there you go. It depends on the axis of rotation. It depends on how far the mass is located from the axis of rotation. Clearly, how far the mass is from the axis of rotation is really important because that part is squared, okay? Doubling the mass would double the moment of inertia. Doubling the distance from the center would quadruple the moment of inertia. So changes in relative position have big effects. When we do our race over here, hoop versus disc, they have the same mass, but they have different moments of inertia. If we're racing down the hill, disc wins. Disc has a smaller moment of inertia, so disc also ends up with a smaller percentage of energy stored in its rotation. Okay? If you want something that stores a lot of energy in its rotation, you want something that looks a little more like this. And so that's a flywheel. I stole this out of one of the elliptical machines in the cardio room. So if you find one of them that's not working today, it's because I have this from it. But pass it around and it looks like a disc, but if you actually like get your hands on it, the disc part is really thin. Most of the mass is concentrated out here at the rim, okay? And that's because the job of this thing is to store energy in its rotation, okay? And that's what causes an elliptical to move so smoothly. So dig that, but don't roll over your phone or your MacBook Air. Question, Mark?
So moment of inertia, it's like it's resistance.
Changes in rotation.
Okay.
Kind of like you can think of mass as being like a resistance to a change in motion. Something that's more massive, it's going to be harder to get it moving and harder to slow it down.
Mm-hmm.
So for something with a large moment of inertia, it's harder to get it rotating, but then it's harder to stop it rotating once it's going.
Okay.
And so the role of a flywheel, like in the elliptical, is to smooth out the motion. in your car's engine, you have a flywheel for similar purposes. You have 4 cylinders. So if you didn't have a flywheel, your car would be very, very jerky. There'd be a lot of vibration. But the presence of the flywheel prevents those sort of instantaneous bursts of acceleration because it resists changes in the rate of rotation. Once that thing is spinning, it kind of attenuates the rotation of the crankshaft. Car stuff, car words. All right, moving along. Calculus. So this is basically like the center of mass stuff the other day. So if I'm talking about a stick and I want to determine its moment of inertia, okay, we're going to have to sum up all the mr squared terms for this thing. So we cut it into really small sections, okay, really, really, really small masses, and we look at the distance of those masses from the axis of rotation, okay. So the x-coordinate at the axis of rotation is 0. The x-coordinate at the other end of the stick is whatever the length of the stick is. As this thing is written, so the moment of inertia is the integral of r squared dm. So that's what we're trying to do here, but integrating with respect to mass sucks. So we're going to try to integrate with respect to length because that's kind of easier to establish bounds of integration for. And I need to go back and revise this. I shouldn't be using dl here. It should be dx. But the long story short that I'm trying to get at is the ratio of the mass of the stick, the total mass of the stick to the total length of the stick, is the same as the ratio of the infinitesimally small mass to its infinitesimally small length. Okay? I'm saying that the density of that thing is uniform. So if I cut a really thin slice of it, it has the same mass per unit length that the stick as a whole has. And then I just rearrange that in terms of dm. The constant mass per unit length here, dl, is going to go in place of dm. And mass per unit length is a constant, so I can pull that out front. And we're going to integrate r squared with respect to the length of the thing. So that's why I probably should call that dx. I don't know. It's just d something with the length of it. And our bounds of integration are from the axis of rotation, so the 0 end of the stick to the other end of the stick, which is the total length. And where this is slightly different from yesterday is now I have r squared in here. So when I go to take the integral of r squared, I'm going to do the same thing. I'm going to add 1 to the exponent. So 2 plus 1 becomes 3, and then I divide by 3. So I get r cubed over 3, and I'm going to evaluate that from 0 to L. So I put in L for r, and I get L cubed over 3. And I put in 0 for r, and I get 0 cubed over 3. So in the end, I'm going to have that constant mass per unit length ratio times L cubed over 3, and I get one of those L's to cancel out. I get ml squared over 3. That's how they get the moment of inertia for a stick about its end. That's a relatively difficult way to rotate a stick about its end like that. Okay? So I'll slap that slide up on the canvas for you here. Let me grab this quick. I'm going to bring it over here into this. So this is saying I stick equals ml squared over 3. If instead we rotate the stick about its center, so we get a really long stick, and we're going to rotate it about its center here. this becomes the axis. The stick still has length L, but where the axis is located defines where 0 is. So if I'm going to try to find the moment of inertia for a stick about its center, I'm going to evaluate that from negative L over 2, right? Because this is half the length to the left, to L over 2. That's half the length away to the right from the axis of rotation. And so that's the only thing that's really going to change here. So M over L, we're going to evaluate that from negative L over 2 to L over 2. The R cubed over 3 thing doesn't change.
Wait,
What'd I do?
I thought you were evaluating the R cubed over 3 from L over 2 to negative L over 2. That's what you did in the last.
In the previous one, I evaluated it from 0 to L.
Yes.
And that was because in the previous one, my axis was on one end of it.
Yeah, yeah.
And so I'm going to go from 0 to L.
But didn't you evaluate R cubed over 3 from L to 0?
So for R cubed over 3, I put in L and got L cubed over 3.
Yeah.
And then I put in 0 and I got 0 cubed over 3.
So the line should be on the other side of the R cubed over 3. That's fine.
Oh, math semantics. I should be putting it over here.
Yeah.
Yeah, help me out with that because I'm going to
Okay.
mess that up all day. All right, so you don't like that there. You like that there. All right, so you don't like this here. You want it
On the other side of
lo siento.
Thank you.
That's like the math equivalent of using the wrong there. I'm so sorry. What's up?
So I'm a little bit confused when you're saying you're substituting x in for like the dx instead of integrating according to L. You're integrating according to x, like you should have written it that way. So how are you pulling out the m over L as a constant? Because right now you're integrating according to L. So like how like so
I'm
like
just not writing it right. So where do you want me to write this
I'm
thing
just
as
like
a
a little bit
constant?
confused because if you're integrating something according to a variable, you can't. That's not a constant, so you can't pull it out. So is like the dl is the L and the dl different from the m, the L and the m over L? What? Okay, I'm confused.
So M over L is like a constant based on the stick
Right.
itself.
I think
So I'm pulling that out front because that's just a number.
I think it's like instead of R cubed, would it be like X cubed and then it's dx?
Sure.
Because then you would plug those in for R. That would make the most
You
sense.
happier here? So this is X and this is DX.
Yeah.
This is X and this is DX.
Okay, that makes sense. Okay.
All right. I don't speak math, so I apologize because I'm in a second language here.
That makes
All right.
it easier to understand.
So the long story long is that I've got M over L, and this is going to be L over 2 cubed over 3, and then I'm going to minus negative L over 2 cubed over 3. And so then we'll do some math here. And M over L, this is going to be L cubed over 8 over 3 minus negative L cubed over 8 over 3. Old's judging me based on my parentheses. Now I'm all math triggered. All right. And dividing by 8 and then dividing by 3 is the same as dividing by 24. So M over L, L cubed over 24 minus negative L cubed over 24. Long story longer, M over L equals, M over L times 2L cubed over 24. Hey, we can get rid of one of those L's, and we will. So this becomes 2ml squared over 24. Hey, buddy, can't you simplify that? Yeah. ml squared over 12. So extremely long story long. It's easier to twist about its center than it is to twist it about its end. How much easier? Oh, quite a bit. Okay. So a stick rotating about its center stores less energy than a stick rotating about its end. And again, on the day, this is about it as far as like the expectation level for what you can pull off. It's being graded by physicists, so where you slap that bounds of integration, it's probably not going to upset them because they don't know either. Just as long as you actually crank out the algebra correctly, that's kind of the important part. So if you can get the math to say ml squared over 12, I'm happy with you. The only integration that you have to do for moment of inertia, though, is with sticks. The rest of that stuff is just known. So you just have to get all Khaleesi with it. Like moment of inertia of a solid sphere about its diameter, well, that's 2/5 mr squared. Well, why is that? It is known. Okay, so that's all you need there. Spherical shell about its diameter, that's 2/3 mr squared. Cylindrical hoop about its center is the biggest moment of inertia. This is like the most energy stored in rotation of any shape you can get, is when you pack the mass as far as possible from the axis of rotation. So mr squared. The disc, the wooden disc there, that would be half as much. That would be half mr squared. Okay? The one that's not listed on here that's important to know, if you think about that circular motion apparatus that we had, or I can just swing this thing around, this doesn't make it all dangerous. If it's a point particle, so like a bob out on the end of a string, okay, that is, again, all of the mass concentrated as far as possible from the axis of rotation. That is also mr squared. Okay, this is just the textbook image of it. These are good things to have in your memory on your calculator on exam day because they're not on the exam sheet. Okay, so if there was some kind of an equation-y type thing that you might want to make a flashcard for, there you go. There's 6 flashcards right there for you. Okay. Typically, and Dan can correct me when I spout total garbage here in a second, typically if there's a problem that requires a moment of inertia, they're going to declare it for you. Okay, so they're going to say, here's a hoop with moment of inertia mr squared, or here's a coin with moment of inertia half mr squared. They would typically tell you, if you didn't have it and you didn't know, you could just write some kind of sentence like, my teacher's clearly incompetent, so I'm just going to pretend that the moment of inertia for this shape is 1/2 mr squared. And then if you carry out the rest of the calculations from there, you'll be just fine. You'll maybe lose a point for not having the correct moment of inertia. But that's kind of what they look like. So that's an important chart to have handy. I don't have the assignment together yet, but we'll have one that'll be due sometime early next week that deals with rotational kinetic energy and moments of inertia. But let's look at a couple of application ideas here. So if we go back to the problem that you had where we're trying to roll a ball down a hill and predict where it's going to land, how wrong was this to assume that all the EK was stored in translational motion at the bottom of the ramp? Do you remember the percentage breakdown? Sure. Mara's got about 30% here. Remember, it was kind of in that ballpark. So I'm going to revise this so that this is EK tran at B, and this is EK rot at B. EK tran is our traditional sort of 1/2 mv squared EK, and EK rot is our 1/2 I omega squared EK. So I'm going to get rid of one of the boxes here and put about 30% of the boxes into EK rotational. Okay, so then I would say mg delta y a equals, actually let me write this out differently here. So I would say EG at A, that's where the energy stored at A, is stored as EK tran at B, that's the translational part, and EK rot at B. So this is mg delta y A. This is 1/2 m VB squared plus 1/2 I omega B squared. Okay, Cool so far? Not making it apparent yet where things are going to cancel. There's some ball bearings. Maybe that's in a tub or something. Let's do it. All right. So a couple of things to simplify this then. So I've got omega squared here. And I've got moment of inertia. So this is where I would have to look up what is the moment of inertia for that shape. We had a sphere. So that's 2/5 mr squared, yeah? And then omega, keep in mind we talked about this over here. Omega is V tan over r. So where I have omega squared, I'm going to put in V squared over r squared. So some nice things are going to start to happen. Now I can get rid of r squared. And this becomes 1/2 of 2/5 m v squared. Who's got a calculator? What's 1/2 of 2/5? 1/5. Okay, cool. So up here, this is going to be 1/2 m v squared plus 1/5 m v squared. Okay, so that's where this came from. So percentage-wise, what proportion of the energy is stored in the rotation? 5/10 plus 2/10, something 10, 7/10, and then that's 30%. Okay, so about 30% stored in the rotation based on that shape. That's what 2/5 that's what 2/10 of 7/10 is going to represent. Question, Coley. Cool. All right. So this would have been the way to get the corrected value for the velocity, because now what I'm going to do is take this over here and mg delta y equals 1/2 mv squared plus 1/5 mv squared. So 5/10 mv squared plus 2/10 mv squared. Let's get rid of mass everywhere. Bye. G delta y equals 7/10 v squared. So 10 times g times delta y over 7. Square root all that. That would be the velocity at v. If no EK rot, it would have just been square root 2gy equals v. But because there's EK rot, it's 10/7 g delta y. Square root of that is the v. It's a little bit slower. Okay? If instead you'd used a different shape, you would just put in a different value for the moment of inertia. So if you had used a hoop, you would put in mr squared. And you would have mg delta y equals 1/2 mv squared plus 1/2 of, again, if it's a hoop, the moment of inertia is mr squared. And so then I'm going to end up with and if it's a hoop, this is basically telling me that half of the energy ends up as the EK tran, and half of the energy ends up as the EK rod. It's going to take equal proportions if I have a hoop. Yo.
So if these equations help us find inertia, why would we do the calculus?
Exactly.
Okay.
Yeah.
Okay.
So you shouldn't have to worry about that other than a stick. And it might be like, hey, how did we get about its end? Or they might be tricky and make it be like a third of the way along the stick.
Yeah.
And so you're going to evaluate from negative L/3 to 2L/3 or something. All right. Is there other stuff on here?
Okay.
So again, larger moment of inertia, harder to spin, harder to stop spinning. And so that's why that flywheel is constructed this way with most of the mass concentrated out towards the end. Another little, let's throw this at you. Speaking of dumbbells, which has the larger moment of inertia about the midpoint of the rod? The connecting rod itself is massless, but you can see the difference in these two configurations. So bigger moment of inertia, what do you got? Algebraically, just sum the MR squareds. Golf? Where are you golfing? Kyle, is that even open? Where's Kyle? Dang it.
And then I'm going to be going tomorrow.
Golf?
No,
Feeder.
yeah.
Teasers. Koba, are you in the pie? Okay. Because I wouldn't. All right. I got 5 of you in. And so again, algebraically, all you need to do is sum the MR squared terms. So look at what you've got in front of you. How far it is from the center?
Okay, so like.
Yeah, not that. That capital R is
Okay.
the length of that rod, but that little r is how far is it from the axis of rotation.
This is 3.
All right, here's where we are at the moment. Looks like 1 vote for A, 7 for B, 2 for C. So leaning pretty strongly towards B. So can you use this idea of summing the MR squareds together to get that dumbbell B should have a bigger moment of inertia? Did work. Dope. And if we hadn't talked about it yet, so like effectively you could think of this as being 2 bobs, okay, that are a distance R/2 away from the center. Or you could think of it as 1 bob, that's 2m, and it's R/2 away from the center. And then for this one, this is going to be m, and it's R away from the center. Did I get it? Did I get B bigger? How much bigger? Factor of 2, yeah?
So does that mean if it's bigger inertia, it's going to be less?
It's going to be harder to get it to rotate. And if it is rotating at the same angular velocity, it's going to have more energy stored in its rotation at a given angular velocity. All right. Otros problemas. Parallel axis theorem. Danny, did you have to pull that last year off? Sometimes this one's really helpful though. So you've got something that's rotating about its center of mass. Okay, this is a hoop. This is going to be mr squared. But there are going to be other times where they're going to configure it so that it's not rotating about its center of mass, so that it's rotating about a pivot that's somewhere else through its shape. Okay, so here's my pivot up here, this rod. To figure out the moment of inertia, and I can assure you it's a lot harder to spin a wheel like that than it is to spin a wheel like that. Okay, but how much harder? Well, parallel axis theorem, basically we're going to have two terms here. One term is the moment of inertia about its center of mass, which is it's a hoop, it's mr squared. The other term, down there in the bottom, what they're saying is you're going to take all the mass in the particle and treat it like it's concentrated at that center of mass and just calculate the moment of inertia for a point particle. That's why it's md squared. So assuming that, like if you look at this, if you're being really nitpicky, the distance d between the center of mass axis and the actual axis of rotation is a little bit less than r, the actual radius of this thing. Okay, so to find the compound or the parallel axis theorem moment of inertia for this thing, it's just whatever you get from the chart for its moment of inertia about its center of mass, and then you look at the distance between the axis that goes through the center of mass and your new axis of rotation. That's your d value. And again, treat it like all the mass is concentrated at that point, so md squared. Parallel axis theorem makes a hell of a lot more sense if you're actually applying it to problems, so I'll throw that at you tomorrow. When would I sum them? I would sum them if I had some kind of a compound shape. So like, if Ethan were to put that hoop together with that disc, so go ahead and like put them concentrically there, bro. So if we end up with like the hoop and the disc concentric there, I would have 1/2 mr squared for the disc plus mr squared for the hoop, and that would be the total moment of inertia for that shape. So that would be like a compound moment of inertia. They just add, just like you would add masses together if you're doing 1/2 mv squared. You do the same type of thing here with moments of inertia. All right. There's an example problem on here as well. Okay, so if I take a stick and I have it rotating about its end and it just kind of falls to vertical here, how fast is the tip of it going at the bottom? And again, this is just going to get Google Docs shared out to you. But a couple of things about this. In terms of the EG, we're going to look at how far its center of mass falls. That'll suffice as far as determining how much energy was stored in the gravitational interaction. So it's not falling a distance L, it's falling a distance L/2. And it all just kind of shakes out from there. You've got a stick rotating about its end, so the moment of inertia is 1/3 ml squared. You put that in place of I, that's how you end up with 1/6 ml squared omega squared in the equation. Okay? So ta-da, ta-da, ta-da. So that's all on there. So there's the last couple slides. And again, it's going to Google Doc this at you. P5 moment of inertia. All right, and we'll get some more practice with that the next couple of days. I don't know where I'm at for time here because we got the thing with the survey. If you wanted to work on mastering a little bit, I can pop around and try to give you a hand. That's a good question. Let me shut off the thing.